Is everything made out of waves? Today, we explore the Fourier Transform. This beautiful equation is a tool that lets us use very simple periodic functions to recreate any sound, image, and pretty much any function you can think of. In this video, we explore the conceptual side, the what it does of the transform. Let's begin with an analogy. Suppose we have a murky mixture of colors like we see here. This is our function input. And suppose we are trying to find the recipe for this mixture of colors. We are trying to figure out what colors were used to make this mixture, and also exactly how many drops of each color were used in this recipe. And that's what the Fourier transform can do. It can take very complicated structures like the outline of this mountain and give us the recipe, the combination of periodic functions, each with their own amplitude and frequency, that can be combined to recreate the structure. Let's take it a step further and use the Fourier transform to try to recreate the entire auditory and visual experience I had when recording this video at the Guadalupe Mountains National Park. Beginning with the auditory experience. Here, our input function is the sound picked up by the microphone. On the vertical axis, we have the amplitude of the sound, or how loud it is. And on the horizontal axis, we have time. Therefore, the movement we see in this graph here is telling us that the amplitude, the loudness, is changing with respect to time. Let's give it a listen and see how the input function changes. What do you think the graph of our output function, the Fourier transform of the input function, will look like? Let's go ahead and look at them side by side while we listen to the forest sounds. Alright, let's take a second to make sense of what we're seeing here. We already know what the axes of G of t represent. Let's focus on G of f, the Fourier transform. Notice that the horizontal axis represents frequency. On the left side of this axis, we have the lower frequencies, and on the right side, the higher frequencies. The vertical axis represents the audio level. You can think of this as telling us how much of a given frequency is present in the signal at any given time. Now, if we pause the video right here, we see a very complicated input function, which again is all the sound that microphone is picking up in that instant in time. If we look over at the Fourier transform side of things, we see that the highest peaks represent the frequencies that are most present in that sound signal. And the lower peaks represent the frequencies that are present but are not as loud. This specific Fourier transform is telling us that a lot of that sound in that instant is being transmitted in around the 6 kHz range, the 1.5 kHz range, and the 0.5 kHz range. Now these surely correspond to the animals we hear the most of, which are the crickets, the crow, and that barking dog. I'll play it back and let you figure out which animal is transmitting sound at which frequency range. This frequency analysis of the sound you just did is often used in sound editing and mixing, where it's sometimes necessary to increase, decrease, or eliminate completely the sound related to a certain frequency. Now let's use a Fourier transform to try to recreate the visuals of this scene. We're going to begin by recreating the spatial properties of this image. That is, all the lines, contours, and curves that we see without any of the color. In this case, I wrote a Matlab script that takes in the grayscale image and produces the Fourier transform of that image. Here, each pixel represents a different periodic function, and the brightness of that pixel represents the intensity or the amplitude of that function. The pixels on the horizontal axis represent periodic functions that only have a horizontal frequency. That means they only change as we move horizontally. The pixels on the vertical axis represent periodic functions that only have a vertical frequency, so they only change as we move vertically. Pixels that are not on either of the axes represent periodic functions that have a combination of vertical and horizontal spatial frequencies. Altogether, the Fourier transform is again the recipe for how to get that original grayscale image from a combination of these periodic functions. It tells us that if we keep combining these periodic functions one after another, the image that is produced by the Fourier transform gets closer and closer and closer to our original image. This is powerful. This is exactly what our computers do when they store images. They don't store every single detail, every single pixel of that image. They convert it to a sum of periodic functions that are much simpler to store. Finally, let's address the color in this scene. Remember that all colors we see are electromagnetic waves with different frequencies, all within the visible spectrum. When light from the sun travels through this landscape, some frequencies are absorbed by the rocks, leaves, gases in the sky, etc. But some frequencies are reflected by these materials. These reflected waves travel through space and toward us. The scenery we perceive is a combination of all these waves entering our eyes. Recall now from our diffraction experiment, linked above, that the light passing through a very small sliver creates this pattern. This is essentially the Fourier transform of the light passing through that tiny sliver of space, where the brightness of the bands represent the intensity of these frequencies, and of course the colors themselves represent the frequencies. This same concept is used by astrophysicists when exploring the makeup of distant planets and galaxies. Using this Fourier spectral analysis, they can figure out what frequencies were absorbed by a planet's atmosphere, and therefore what gases make up that atmosphere. And that about concludes our conceptual exploration of the Fourier transform, a beautiful mathematical tool that allows us to find the basic ingredients for sounds, images, planet atmospheres, and pretty much any continuous function, no matter how complicated. I'll explain the how of the transform and get into the nitty-gritty of the equation itself in another video. In the meantime, I'll drop a link to a video by 3 Blue 1 Brown into the description that does a great job at this. Peace, y'all. See you next time.